Hi, in this lecture we are going to talk about the concrete implementation of the merge sort, so let's get started. Basically, we have been talking about in a theoretical section that this is a divide and conquer algorithm, which means that there are going to be recursive method calls, and that's why we have to define the base case first. This is what we have been discussing as well, that we keep splitting the array into smaller and smaller subarrays until we bump into the situation when the size of that given array, so the length of the nums array, is equals to 1. What does it mean? That given subarray contains only a single item. This is when we return, which means that we consider that given array to be sorted. Of course, because there is just a single item. And anyways, we have to generate the middle index and we have to create two subarrays, the left subarray as you can see and the right subarray, and we have to call the merge sort method recursively on the left subarray and the right subarray. So this is the so-called divide part that we have the one-dimensional array of integers. We are going to generate the middle index and we are going to call the same method recursively on the left subarray and the right subarray. And of course we keep splitting the left subarray and the right subarray as well, so that's why we are going to split the left subarray and we are going to split these arrays as well until we have just a single item left in these given subarrays. So this is why we are going to split the arrays and keep calling the merge sort recursively until we bump into the base case. What does it mean? That we just have a single item left. So basically this is the divide part and we have the conquer part. What does it mean? That after splitting the arrays into smaller and smaller subarrays, we are going to have subarrays that contains just single items, and then we have to merge them until we end up with the sorted array. So this is the conquer part. We have to define three indices, I, j and k. The I index is going to track the left subarray, the j index is going to track the items in the right subarray, and the k index is going to track the items in the result array. And this is why it is not going to be an in-place algorithm, because we need some additional memory. Okay, so this is why, as you can see, we have I, j and k. What does it mean? While the I is less than the length of the left half and j is less than the length of the right half, that we have to consider every item from the left subarray or the right subarray. And if the item in the left subarray is smaller than the item in the right subarray, we are going to insert it into the nums array. Okay, and of course we have to increment I, because I tracks the left subarray. So we insert the item from the left subarray, that's why we have to increment the index of the right subarray. Else, we know that the item in the right subarray is greater than the item in the left subarray, so we insert it into the final result array and we increment the j index which tracks the right subarray. And finally, we have to increment k, which tracks the result array. So this is what we have been discussing, that we keep comparing the items. 1 is smaller than 3. The right subarray has something to do with the j index. The left subarray has something to do with the I index. In this case, we insert 1. And of course, we have to increment j, because we have to keep going and keep comparing the items accordingly. And of course, on every time we insert an item into the result array, we have to increment the k index, which tracks the result array. In this case, 3 is smaller than 4, we insert it into the result array, and we have to increment the index I, as you can see, and of course index k. So this is what's happening here. And what about these parts? If we have items left in the left subarray, we have to copy all the values into the result array. And if we have some leftover in the right subarray, then we have to copy all the values from the right subarray. So we keep comparing the items, and as you can see in this case, okay, let's insert 6, let's insert 8. In this case, we have some items in the left subarray when we have already considered every single item from the right subarray. So that's why in this case we have to copy all the values from the left subarray into the result array. And of course the same situation can occur in the right subarray, which means that we have considered every item in the left subarray and we have some leftover in the right subarray, so we have to copy those items. So this is why we have these two while loops. If we have already considered every item from the right subarray, we have to copy the values from the left subarray, and if we have considered every single item from the left subarray, then we have to make sure that we copy all the values from the right half and right subarray. Okay, so basically that's all about merge sort. Let's try to sort, for example, 2, 5, 4, -1, 0, 1. Let's save it. Okay, let's call python merge.py, and as you can see, -1, 0, 1, 2, 4, 5. -1, 0, 1, 2, 4, and 5. So basically we have managed to end up with a sorting algorithm that's capable of sorting one-dimensional array of integers. So this is how merge sort works. We have a divide part and we have a conquer part, because this is a divide and conquer algorithm. Thanks for watching.